Sean, thank you very much for being here today, for taking the time. I will play your presentation.
Good morning. I'm Sean Hanna, Professor of Design Computing at the Bartlett, and I'm very pleased to be here, virtually at least. And for me, it's a kind of a chance to show a little bit about my own work, the work of my colleagues in my lab, but really to think about it in context, to think about what it means in relation to how we design and how we deal with models of our world. I've called it the black box of design computation. And I'm focusing, as I said, on how we deal with the models that we use in design. I'm going to start with this. This is a relatively old architectural drawing. Whenever you get a drawing like this, the first thing that strikes me is just how little there is in terms of information. I mean, this is quite a complex drawing. You can see it's quite detailed and so on. But compared to the amount of information that we currently have when building a building, the documents that you see from a building, say 100, 120 years ago, as this one is relatively sparse. Now, one of the reasons for that, though, of course, is that a lot of the information in actually going to construct this particular building was in the heads and in the hands of the people that put it together. It was spread out throughout the whole chain. Now, you'd have many craftspeople involved. You'd have a mason who would know what to do in terms of reading this drawing and turning it into quite sophisticated and detailed stonework. But you didn't need quite that much information specified by the architect, because that information was there. It was in the people. They knew their jobs, and they knew, based on precedent, what they could do. Situation has changed, though. We have a lot of new demands in terms of our buildings now, in terms of sustainability, in terms of performance, things like that. And we have new technologies, many new, very complex technologies that just didn't exist 100 years ago. And for a lot of this, there's no precedent for it. There's nothing to base it on. So we have to specify quite a lot up front. And now, of course, we build that into a model. Our models have become bigger and bigger. We have quite sophisticated tools for doing so. We can plan much better with these models. We can be much more efficient, and we can avoid costly mistakes. So by building, say, a BIM model and specifying all the information that normally would have been just taken for granted, designers are now becoming the coordinators of all this vast amount of information. Now, this is beneficial, but there are potential problems with this. As you can see from this diagram, there's a big difference between something 100 years ago, where all of that information, all that knowledge is spread out all the way along that process, and what we have today, when we're concentrating all that knowledge up front. Now, this is a bit of a warning, I suppose, as to building too much into your model. This is on Rigor in Science by Borges, about a college of cartographers that are involved in drawing bigger and bigger maps of the empire. And eventually they get bigger and bigger, and they contain more and more information, that they end up making a map that's a one-to-one scale map of the empire, and it coincides with it point by point. Now, of course, this is completely useless as a map. It's too big, it's too cumbersome, there's just too much in it. It can't help you navigate. So, of course, that's the end of the science of cartography. Now, the thing is, we do this too. We always have in computation. It's just the way that computation tends to work. To give a very condensed timeline here, this is going way back to the beginnings of the first calculating machines. There's always been an idea that we can faithfully model the world in arbitrary symbols. Newell and Simon said this very well in the 20th century about the physical symbols hypothesis, that the idea of AI is essentially to find the right kind of symbol systems. And this is much of what AI is set to do, to craft this model. Also implicit in this idea is that there could be one single model that would suffice. And a very similar thing is the case when we come to design computation. So when we come to making, say, the digital twin or the building information model or even the parametric model, the idea is that we come up with one single model that is meant to represent the building or the thing that we're designing. Now, that's very useful, of course, but we potentially end up in the same dilemma as Borges cartographers. Now, Of course, another alternative to artificial intelligence is, of course, the machine learning side of things. So starting from data and machine learning rather than starting from that model of the world and then crafting the model from that. Now, that's where my work sits, and through it, we can do a number of things. So I'll give a few examples of this, of course, the examples of work from my students, my lab, and my own work that obviously don't cover everything, but give some sense of where machine learning and AI sit in the context of design. This one, of course, is, as you can probably see, some computational fluid dynamics. Sam Wilkinson's PhD thesis looked at this, and it's a case of very, very complex patterns of movement that you can simulate using computational fluid dynamics or wind tunnels if you have the resources. But of course, this is very difficult to do at early stages because the computation time is it's extremely cumbersome, it's intense, and it takes a long time. So what Sam looked at was using machine learning to try to approximate models of computational fluid dynamics. So if you have a building in the context of a very complex environment, surrounding environment of a city here, that is an extremely difficult model. It takes a long time to calculate, but by using data from previous models and using a particular type of representation of the geometry, you can actually distill that problem to something that's quite a bit simpler. You can come up with a model that is able to replicate and make a very good approximation of the output of a computational fluid dynamics simulation. Now, in the end, you get something that is either faster or better than any explicit simulation of computational fluid dynamics. David Hawkins' work looked at using actual post-occupancy data of energy use in real buildings. He was able to train a neural network to estimate energy use that was dependent on factors that are actually under the control of the designer, like glazing or building orientation. And the predictions were between 25% and 40% more accurate than existing benchmarks. So this is both of these